Chapter 9, Section 1, please. The reason I spend so much time working on relations in general is this final idea, equivalence relation. I want three properties. Those are the three properties I'm after. A relation that is reflexive, symmetric, and transitive on a set, so from A to itself, is an equivalence relation on A. Put that word in here, on A. In a real sense, this is a foundational piece of most higher mathematics ideas. But let's look at some examples. You've seen some of these before. Some other ones I'm going to make up on the spot. I want to look at words. I'm going to define a word as any string of English letters. Whether it makes a real word in English or not is irrelevant. I don't care about case at the moment. Uppercase, lowercase, we're just going to assume they're all the same. Two words, two strings of English letters, are related if the length of the first word is the same as the length of the second. Okay. Let's check our properties. Is this relation reflexive? Seth, you're nodding your head. Tell me why. The length of A is clearly the same as the length of A. Again, sometimes this is, well, of course it is, man. Duh. I get it. All right. Is it symmetric? Emily, why?
Because if A has the same length as B, then B has the same length as A.
Okay. How about transitive? Why? Same exact idea. I'm going to write a symbol. L of A is the length of the string A. I should have written this earlier because then I could make these statements much shorter. If the length of A is equal to the length of B and the length of B is equal to the length of C, then, well, yeah, length of A is equal to the length of C. Exactly what we wanted. Okay. This is an equivalence relation. On our set of strings of English letters. Mhm. Another example. Let's look at a set of integers. A is related to B if and only if A is congruent to B mod M for some fixed positive integer M. Let's even go a step further, bigger than 1. I need you to prove my 3 properties. I just don't want to nod my head, go, well, of course it is. Explain to me why. That's a proof. We're proving stuff about integers. And best part, we did all these proofs back in chapter 4, where we first introduced mod. So you've seen all of these answers. I just have to remember them. Crap. How do I dig this out of the brain pan? Let's go find it. All right. Recall A is congruent to B mod M means what? What does it mean to be congruent mod M?
A mod M.
Yes, but that's not anything other than restating what that word is up there. Can you state it without using the word mod in it?
A divided by M.
Well, no, A divided by M may not have a remainder of B, because A divided by M may have a different remainder. Well, no, A divided by M will have a remainder, but B might not be that remainder. I'm closer though. Dominic?
I was thinking like A divided by M, the remainder would be the same as B divided by M.
So A divided by M and B divided by M have the same remainder. How can I write that algebraically? And that's what it is in words. I'm still not sure I like that.
Maybe do A divided by M minus the floor of A divided by M is equal to B divided by M minus the floor of B divided by M.
I like that better. I like that better. But if I'm doing that, what I'm really saying, then with A divided by M minus floor of A divided by M, that's a non-integer, right? That's a fraction. I'm saying the fraction is the same as the fraction. I don't want to deal with fractions at the moment. I want to keep dealing with integers. So I'm closer with that definition. Right? Can I get it out of fractions and back into integers? Right?
If you do like A divided by M minus the floor of A divided by M, multiply that by M.
Which would give me an integer. And then I would do B over M minus the 4B minus, and that would give me another integer, right? But I'd have all these multiples by N, right? Multiplying by M. We got around that. If I take those two sides, they should be the same, right? So if I subtract them, I should get 0. So what if I just took A minus B? What do I know about A minus B? It's a multiple of M. Now I have a process that has nothing but integers in it and deals with A minus B when I'm looking at A minus A, A minus A and B being related, right? If I want to look at A and B, I look at their difference. So that, I think, is the way to attack this problem. This is actually one of our definitions for congruence back in chapter 4. The difference between the two numbers is a multiple of that, because that means the remainder would be the same. A would be some number of m's plus a remainder. B would be some number of m's plus the same remainder. B might not actually be smaller than m, which is why I don't know if it's the remainder, Ian. But let's use this. Is R reflexive? I want to know if A is related to A. And 0 is 0 m's. A minus A is some number of m's. A is related to A. How about symmetry? Well, symmetry is an if-then. So let's say if A is related to B, then what? What does that mean? Yeah, but that means this, doesn't it? Okay. I want to show that B is related to A. But if I want to show that B is related to A, I need to be looking at B minus A rather than A minus B. Yes? Isn't that a true sentence? To get from B minus A to A minus B and multiply by -1. Isn't that a multiple of M? It's the negative of the previous multiple, but that's still a multiple of M, and this is still an integer. Yay, it satisfies our underlying definition. So B is related to A. I started with A is related to B. I got B is related to A. That's what symmetry means. I'm thrilled. Now for the big one, transitive. Again, transitive is an if-then setting. What's the if?
If if A is related to B and B is related to C.
Okay, so let's start with that if. Suppose A is related to B and B is related to C. So A being related to B means A minus B equals Km for some integer K. B is related to C means I got to be careful here. Yeah, I don't know if it's the same integer, right? That means that B minus C is Lm for some L in Z. What is my, if A is related to B and B is related to C, then
A minus C equals M.
A is related to C. Somehow I got to get A and C to make this obey, right? So now I got to look at A minus C. Well, crap. I don't have anything about A minus C. I have A minus B, B minus C. I don't have A minus C. How do I get there from here? Because if I rearrange the parentheses, the minus B and the plus B cancel each other out. Son of a. Which means this is Km plus Lm, which is, I can factor out an M. And K plus L is still an integer, isn't it? So as a conclusion, I now know A is related to C. It's reflexive, it's symmetric, it's transitive, it's an equivalence relation. On our set. Our set happens to be the set of integers, so I just write on the set of integers rather than on the set A. Questions? I know it's not all that long ago, but we were doing class registration, right? What day were you allowed to register on? We had a list. How did we break down the list? How did you know who was allowed to register when? And that was based on the number of credits you'd earned. I don't remember what the first day of registration was. Yeah, I don't remember the date. It doesn't matter. Let's make something up and say you could register on May 1st if you were a senior and you had earned 91 or more credits. You were able to register on the 2nd or the 3rd or the 4th, right? I could break this up. Oh, graduate students came first. I apologize to all of the graduate students. Graduate students on the 1st, seniors on the 2nd, juniors on the 3rd, sophomores on the 4th, freshmen on the 5th, non-degree seeking students on the 6th. I made the days up out of whole cloth. So, is this reflexive? I can register on the same day I can register, right? And if Divine and Dominic can register on the same day, then Dominic and Divine can register on the same day. That's symmetry. Transitive. Nicole, if you and Emily can register on the same day, and Seth, Emily and you can register on the same day, then Nicole and Seth can register on the same day. It's transitive. Is there any math to do in this one? But if you write out the words, you can argue it. Perfect. This is an equivalence relationship on the collection of students at Seton Hill. But Emily, you said we divided it up based on what year you were. We actually don't divide it up based on year. We divide it up by credits earned. So what you call a junior is someone who has completed at least 60 credits and not more than 89 credits, right? 61 to 90 or 60 to 89. I don't remember where the dividing line is. But it's one of those groups, right? The word junior is a set within A. The set of all elements of A, which are equivalent to A, under some equivalence relation, is called the equivalence class of A. And we would usually write it like this. Square bracket A sub R. R is the name of our equivalence relation. And we could define this as a set. The set of X in R such that the set of X in A such that A is related to X. A itself is a representative of the class. So, in terms of students at Seton Hill, I have 6 categories of students. I have graduate students. I have seniors, juniors, sophomore, freshmen, and non-degree seeking students. Students who are just to take one class or something that are actually after a degree. And if you look at the registration paperwork, which you can still find on my shoe, it tells you what day you're allowed to register based on which of those 6 classes you're in. I don't know who's what in this room, but that's not the point. I could say, if you are able to register on the 3rd day, graduate students, seniors, juniors, if you're a junior, that's a group, right? But just look at in this room, I could pick one person. All of you are equivalent to this junior. That's my class representative. You just created a subset for me. We had 2 other equivalence relations. Let's go back and look at our equivalence relation on length. We're using that length idea, right? So here's my question. What are the equivalence classes of the set strings of English letters under this relation? Two strings are equivalent if they're the same length. If I ask you to describe an equivalence class, how would you do it? Oh, your brows all filled up. Talk to me.
Class would be marked just by.
All of the single letters, class of words of length 1, all the words of length 2, words of length 3, words of length 5, we missed one. We missed a class. Words of length 0. There's only one item in that class, right? The empty word. Here it is. Oh. So I have an equivalence class for every natural number under this relation. Somebody pick for me a positive integer bigger than 1. I'll go with 5. 2 is too small. So this is our mod m relation, but we just picked m to be 5. How would you describe the equivalence classes? Seth?
One class where it's all the integers which take the form of a multiple of 5 plus 0. And another one where it's multiples of 5 plus 1 plus 2 plus 3 plus 4.
Every integer has to be somewhere in that one of those sets, right? No matter what integer you pick, positive or negative, that doesn't matter. They got to be in one of those. So I would then call these by a representative. So let's pick a number in each of these classes. I could say that this first class, I'm going to call that the class 0. And I'm going to call this one the class 1. And this one the class 2. And this one is the class 3. And this one is the equivalence class containing 4. And thus, I can really say that as far as I am concerned, there are only these 5 classes to work with. Might as well call them 0, 1, 2, 3, 4. Hey, wait a second. What if I picked a different number? Somebody give me a different number other than 0 that's a multiple of 5. 10. I could just as easily have called this class 10. Once I have picked a representative, the representation is not unique. By default, I picked the smallest non-negative number, but it's not required. Huh. That's a set. So is that. What's their intersection? Why?
Does that have to be one or the other? It can't be both.
I want you to explain why that's true. Why can't we be in both?
You can only either be congruent to 0 or be congruent to 3. You can't be congruent to both.
I will say it again. You've just restated the sentence. Tell me why I cannot be congruent to both. No, no, this is based on this mod's idea. This is this one.
If you have something times 5 plus 0 and then it plus 3, they can't be the same number.
Aha. 5 something plus 0 equals 5 something else plus 3. Then the difference is a multiple of 5. No, the difference is 3. Oops. There's my contradiction. The remainder, when I divide by 5, can't be 0 and 3 at the same time, because that would tell me 3 is a multiple of 5. 3 is not a multiple of 5. As a matter of fact, there are only 2 possible results when I do the intersection here.
It's either empty or it's everything in A.
Because either those 2 congruence classes are different or they're really the same. Now, Santino, you're not wrong about your sentence. If I go back and I look at the one about what number of credits you've earned, right? If the division between being a sophomore and a junior is did I earn more than 60 credits, I either earned more than 60 or I didn't. I can't do both at the same time. I can't be in 2 classes at once in terms of groups of students. Oh, I've used this abbreviation before. What does TFAE stand for? Been a long time since we've written this one out. The following are equivalent. We did this back in chapter 1, section 7 or 1, section 8. I can use 1 to prove 2 and 2 to prove 3 and 3 to prove 1. So if one of them is true, they're all true. If one of them is false, they're all false. Now, it turns out that this is actually a direct proof from 1 to 2, from 2 to 3, from 3 to 1. But that's less important in this case. The proof is in the text on page 643. Yes, 643. But this is the headline. I don't need to read the article at the moment. Questions? Emily, you're looking at this like it's bothered you or it owes you money. I can't tell which.
So A is in relationship to B. A,
The equivalence class of A,
class of A is equal to the equivalence class of A,
of B.
or of B, and then
The equivalence class of A and the equivalence class of B have a non-empty intersection. They have something in common. As soon as they have something in common, they have everything.
because they're either 0 or they're the same. Got it. Okay.
So it suffices to show that they just have one thing in common, and then you know they have to be the same. But wait a second. If I'm looking at the integers mod 5, or if I'm looking at the students divided up by class, or if I'm looking at strings of English letters by length, then every student, every string, every integer must fall into a class somewhere, right? And this theorem tells me that those classes are separate or identical. Anytime I look at two classes, I've either picked up two completely disjoint sets or I picked up the same set twice. Let's consider the example with we were doing the integers mod 5. In Z, using this mod 5, we had 5 classes. I could write out every single integer. And they would have to be in one of those groups. And if I took the union of all 5 of those sets, what would I get? All the integers. And I would have counted each one only once, right? So those are 5 disjoint sets whose union is all of our universe of discourse. Humble. Roll a 1. Sorry about that. If I pick any set, a partition of S is a collection of non-empty, disjoint subsets of S. I need to give them names. Well, we'll do that next. Whose union is all of S. A partition of S breaks the set up into a bunch of non-empty piles where no pile contains anything in common with any other pile. Let's call the sets S I they're all non-empty. If I pick up two of them and they're different, then their intersection is empty. And the union over all possible values of I of SI is all of S. That's the three conditions I need to say I have a partition. The sets, equivalence class of 0, 1, 2, 3, and 4, are a partition of the integers, mod 5. The class designations, graduate, senior, junior, sophomore, freshman, non-degree seeking, is a partition of students at Seton Hill. The numbers 0, 1, 2, 3, 4, 5, ... is a partition of words in the English language by length. Questions? In a way, I can think of my giant set S and I've carved pieces off of it.
So for anything in these subsets, they have to be uniquely in only one subset.
Each element appears in one and only one subset. None of our subsets are empty, and our subsets are exhaustive. They cover all of my set. We do this in probability and statistics a lot. The null hypothesis and the alternate hypothesis are mutually exclusive and exhaustive. So what? Big deal. Why do I care? Maybe. Yes. No. Partitions and equivalence relations are the same thing. A partition on S, partition of S, creates an equivalence relation. How? Two things are equivalent if they're in the same partition cell. So I could give you a partition of the integers. Ready? I'm going to name all of the integers into a finite number of subsets. The odd ones and the even ones. Isn't that every integer? Odd ones and even ones? Which one did I miss, Seth? 0 is even. When you divide it by 2, you have a remainder of 0. 0 is even. I got all the even ones, I got all the odd ones. Are there anything? Are either of those sets empty? You can name an even number, you can name an odd number, fine. They're not empty. There's no intersection. A number's either odd or even, and it's exhaustive. We covered all the integers. That's an equivalence relation. I didn't build it as an equivalence relation, but it is an equivalence relation. How do I know if two numbers are equivalent? Two numbers are equivalent if they're both odd, or if they're both even. That's the same as if they're the same mod 2. That's the equivalence relation for the partition I was given. I'm going to define the integers, partition them up a different way. I'm going to partition up the integers from minus 100 to 100 inclusive, from minus 101 to negative 1000 and 101 to 1000. That's group 2. And then from 1001 off to infinity, minus 1001 down to negative infinity. That's group 3. I have small and medium and large. Is there any overlap? Are any of the sets empty? That's an equivalence relation. I covered all the integers into a partition. Two integers are equivalent if they're both small, or both medium, or both large. By my definition. As soon as I created a partition, I created an equivalence relation. If I give you an equivalence relation, you've automatically created a partition. Just find the classes, and you've got the sets in your partition. By the way, an equivalence relation is reflexive, symmetric, and transitive. I wonder if there would be a nice, easy way to look at the digraph or the matrix for our relation and determine whether or not it was an equivalence. I already know how to check for reflexive and symmetric, right? Transitive becomes the hard part. But if it's partitioned, then here, I'm going to make up a partition on a set. Ready? My set S is 1, 2, 3, 4, 5, 6. My partitions are as follows. Set 1 is just the number 1. Set 2 is just the numbers 2 and 3. And set 3 is just the numbers 4, 5, and 6. One is related to 1 and nothing else. 2 is related to 3. 2 is related to 2. 3 is related to 3. 4, 5, and 6 are all related to each other, right? What's the digraph look like? It's blocked off into 3 separate pieces. It's partitioned. The matrix is 2. If you make the matrix for this relation, 1, first row, first column has a 1 in it. The rest of that row, the rest of that column are zeros. Second row, 2 and 3. Third row, 2 and 3. The rest of those rows and columns are zeros. 4, 5, 6. I've got a block 3, 3, 3 ones in each row. Block behavior. There's a nice way to tell. Equivalence relations give me very pretty matrices. Very pretty digraphs. These build a lot more. Question?
So it's like a vertical line test. Like if there's 2 1s in the same column, that means it's automatically not on the.
No, because 2 and 3 both had a 1 in it, right?
Okay, maybe.
I got to look at the way it's blocked up. Please note, 9-3 and 9-5 are both due on Monday. At which point I will answer any questions you have about the final exam, which is on Wednesday. I will see you all then. Have a wonderful weekend. If you came in late and have stuff for me, I need it.